To say good evening and welcome you all to this evening's Capital Science Lecture. Tonight's event is jointly sponsored by Carnegie's Department of Terrestrial Magnetism and the National Aeronautics and Space Administration. And before I introduce our lecturer, I'd like to invite Dr. James Green, who is the director of NASA's Planetary Science Division, to provide a few words of greeting. Jim?
Well, thank you very much. It's a very special occasion. We're really in for a treat. Maria Zuber has been professionally focused on the structure and tectonics of solid solar system objects. And she's really quite well known in our field. She's been involved in more than 10 NASA missions. The one we're probably going to hear the most about tonight is the Grail mission. Maria has been the principal investigator of two spacecraft that orbit the moon that we'll hear a lot about tonight. She is our first woman principal investigator, and she's truly amazing. I really view her as someone that has made miracles happen, and she makes it look easy. Maria brought in that mission on schedule, two spacecraft that she put together, and even gave NASA back some money. So yes, absolutely. So, but Maria's fame in science pales in the comparison of what she's done, I believe, in many other ways. She teamed with Sally Ride on an absolutely spectacular education and public outreach activity on the Grail mission, and I hope perhaps we'll hear a little bit about that. Maybe not, but in any event, she and Sally ran a contest for middle school age children across the United States to be able to name the two spacecraft, and a fourth grade team, I believe, won Ebb and Flow as two beautiful names. She and Sally also had a wonderful instrument called MoonCam, which allowed students all over the world to select places on the moon to be able to be imaged and then talk about what they see. Truly a spectacular event. Now, I believe firmly that one of the major goals that Maria has in doing this is to bring more of our kids along, more male and female students involved in the science program. But she's such an inspiration to our female students. And in fact, I believe one day I will not have to say that she's our only principal investigator, because Maria personally will make sure that there are other women that move ahead and become principal investigators to these very complicated missions. So once again, we're in for a treat. I don't want to take any more of Maria's time and turn that back over.
Thank you, Jim. We're really pleased to join forces with NASA for tonight's program. The moon has accompanied Earth in its orbit around the sun for billions of years. It likely sprang from the Earth, literally, when a smaller body collided with a planet shortly after it formed, shooting debris into space that coalesced to form the moon. The moon was presumably in place when life first arose on Earth. It certainly was there when humans appeared, and ever since it has been a part of human mythology and science. Early humans associated the moon with gods and goddesses. They devised calendars to follow the moon's motion. They studied how that moon influenced the tides, and they thought, and some still do, that the moon influenced human actions. Robert Louis Stevenson's story of Dr. Jekyll and Mr. Hyde may have been inspired by the acquittal of a London murderer who claimed he was under the spell of a full moon. Certainly, the enduring myth of werewolves attests to the power of the moon's hold over our collective imaginations. By the late 19th century, scientists knew that the moon was a rocky body pockmarked by meteorite impacts. They mapped its visible surface. Not until 1959, however, with the launch of the first lunar probe, did humans see the dark side of the moon. Since then, scientists have sent many missions to the moon. About 24 have landed, some gently and gradually, 6 with astronauts aboard, and some, like the mission we will hear about tonight, with a deliberate crash. The goal of the mission, as Jim has indicated, was called the Gravity Recovery and Interior Laboratory, or Grail mission, was to study the interior of the moon by mapping its gravitational field. The mission was launched in 2011 as part of NASA's Discovery program, an effort to learn more about our solar system through a series of highly focused, relatively inexpensive space missions. Grail's twin orbiting spacecraft, as Jim indicated, Ebb and Flow, made the first demonstration of precision formation flying around another planet. The data they gathered are leading to a new understanding of the moon. Our guest tonight, Dr. Maria Zuber, was Grail's principal investigator and is one of our nation's premier planetary scientists. She has been associated with more than 10 NASA missions over the past 2 decades. Although NASA can rightly call her one of their own, she has been a senior researcher at NASA's Goddard Space Flight Center since 1994. Dr. Zuber's home base is MIT, where she is now Vice President for Research. She is also the E.A. Griswold Professor of Geophysics in the university's Department of Earth, Atmospheric, and Planetary Science. Her interests include the theoretical modeling of geophysical processes, the analysis of altimetry, gravity, and tectonics in determining the structure and dynamics of planetary bodies, and the development of space-based lasers and radio systems. After receiving her BA from the University of Pennsylvania and her SEM and PhD degrees from Brown, Dr. Zuber spent several years at Goddard, where she was the co-leader of a team that designed the first laser altimeter system for Mars. She moved to Johns Hopkins in 1991 and then to MIT 4 years later. She is a member of the National Academy of Sciences and the American Philosophical Society, and a fellow of the American Academy of Arts and Sciences. She is currently serving in both the National Science Board and the National Research Council's Governing Board. Her many awards include NASA's Distinguished Public Service Medal, the Harry H. Hess Medal of the American Geophysical Union, the G.K. Gilbert Award of the Geological Society of America, the American Astronomical Society, Planetary Society Carl Sagan Memorial Award, the Buzz Aldrin Space Exploration Award, as well as Malta NASA Achievement Awards. It's really quite astonishing. In 2002, Discover magazine named her one of the 50 most important women in science. In 2008, U.S. News and World Report, in conjunction with Harvard's Kennedy School, named her one of America's best leaders. Dr. Zuber is an outspoken supporter of NASA's space exploration program and has testified many times before Congress about the organization's future and priorities. She is a champion of space science education in middle schools across the country, and as part of that effort, Dr. Zuber made sure that cameras attached to Ebb and Flow included an opportunity for operation by students. I ask you to join me in providing a warm welcome to Dr. Maria T. Zuber.
Okay, thank you so much for that wonderful introduction. It's so fantastic to see such a room that's full of people who want to hear about the moon, okay? You are my kind of people, and we are going to have some fun tonight, okay? All right. Okay, so let's get started. Virtually every human who has had the gift of sight has looked at the moon throughout history. It's something that binds us together, really, as a people. All of us, I think, can think of times when we've gone outside at night and looked up at the moon and thought about how beautiful it is. And my goal tonight, really, is the next time that you go outside and look at the moon, that you think about it in a different way than you have so far. The moon has been important throughout history. This is a picture that I took yesterday morning. This is the old belfry in Lexington. And these early risers are taking turns ringing the bell, calling the Minutemen to assemble for the reenactment of the Battle of Lexington on the Lexington Battle Green. We don't know all of history. There are a lot of gaps in the historical record, but we know that the weather on the morning of the Battle of Lexington was actually pretty nice and pretty clement. And so it may, in fact, have looked at the time of the battle the way it looked yesterday morning. So we understand some aspects of the history. In trying to reconstruct the history of planets, there are also gaps in the record. We have little bits of information. We know some things, we don't know others. In trying to reconstruct things about our own history on Earth, sometimes it helps to look someplace else. And a lot of the historical record from a geological sense for that is not preserved on the Earth is preserved on the moon. So let's start back in time with Galileo and begin at the dawn of recorded observational lunar exploration. This is a picture of Galileo in his garden in Padua, looking up at the moon through his telescope with 20 times magnification. And from the drawings, you can see here that Galileo saw the highlands and the Maria on the moon, so realized that there were different terrains on the moon. These dark areas he called Maria, just like my name. It's the Latin word for seas. Early on, it was believed that they were oceans. They are not, in fact, oceans. But the material that forms the Maria actually has a similar composition to the material at the bottom of the Earth's ocean floor. So there actually is some analogy there. And so for many years, we had telescopic observations of the moon. We saw that the moon was full of craters. We did not know what these craters were due to. There were thoughts that they were volcanic. There were thoughts that they were impact. And the matter actually wasn't settled completely until astronauts brought samples back to the Earth. Okay, so let's fast forward again. This is an image. This is actually the first image taken of the moon from a US spacecraft. This is Ranger 7. This image is about 360 kilometers across. You can see the craters on the moon here. And the next slide right here, this shows an image that was taken also by Ranger 7 and beamed to Earth 2.5 seconds before Ranger 7 crashed into the moon. Okay. This mission was a success. Okay. In those days, we could get to the moon. We didn't know how to stop. This mission was preceded by 13 other US missions to the moon, which failed, okay? None of which accomplished their goal. So between 1959 and 1964, we had 13 failures, and then success was judged by being able to get your image down 2.5 seconds before you crash into the moon. Okay. 5 years later, we changed our definition of success. This is one of my favorite pictures of the moon, actually. This is Surveyor 3 in the foreground. And this is the Apollo 14 lunar module, Apollo 12 lunar module, excuse me, in the background. And this is astronaut Pete Conrad. And we landed Apollo 12 right near Surveyor 3 because we could. And so in just 5 years, we went from not being able to stop to being able to land anywhere we wanted to. And so the landing of humans on the moon, not surprisingly, is viewed by many as one of humankind's greatest achievements. We brought back hundreds of pounds of rocks. These lunar samples are a treasure trove that are priceless. And these samples are still analyzed today because instrumentation continues to improve. And we continue to make significant discoveries from those lunar samples, which the combination of the samples, the in situ exploration on the surface, and our orbital assets are allowing us to put together quite a remarkable holistic picture of the history of the moon. Okay, so let's talk a little bit about what we know about the origin of the moon. Okay, just like the historical record back at the Battle of Lexington was incomplete, the geological record of the earliest history of the Earth and Moon is quite a bit even more incomplete. There is only one theory for the formation of the moon that doesn't have a fatal flaw, okay? And that is the idea that there was an impact into Earth which formed the moon. And I'm going to show you a video of this, but first I want to say something about the fact that this is a theory, okay? The scientific definition of a theory is quite a bit different than the colloquial definition of a theory, okay? Because you will hear a lot somebody say, well, it's just a theory, okay? In science, a theory is an idea that has been repeatedly tested scientifically and has withstood those tests, okay? It doesn't make it correct, but it accords it a special place in science that makes people want to test it, okay? And it gets adjusted. And in fact, I'm going to show you that our idea of the origin of the moon, the Earth-Moon system, is being adjusted today. So the idea of what we thought happened initially, and we'll take a look at this in just a second here, is that just after the Earth formed, a Mars-sized interloper got in the way, made a strafing hit at the Earth. The core of the impactor wrapped itself around the Earth's core, and material from the mantle of the impactor and the Earth was thrown off and assembled in lunar orbit. Okay, and okay, don't blink. Okay, so here's a computer simulation. This is a smooth particle hydrodynamic simulation of that impact that was done by Robin Canup. And here red is hot, so the Earth largely melted. A great deal of material was thrown off, and the core of the impactor wrapped itself around Earth core, and that is used as an explanation of why the moon has very little iron in it, whereas the Earth has a great deal of iron in it. Okay, so let's talk a little bit about the rocks on the moon without getting into a whole lot of detail. These white rocks here correspond to what we now call the lunar highlands. This rock is a silicate, oxygen-rich rock referred to as anorthosite. Anorthosite, the major metal in anorthosite is aluminum. It's an aluminum-rich rock, and aluminum's going to come into our story a little bit later on. But aluminum's a pretty light metal, and so this rock has a very low density. And in fact, bringing back samples of this anorthosite by the Apollo astronaut actually led to the idea of the lunar magma ocean, and that is that the exterior of the moon was largely melted, and these white rocks here were essentially the scum on the pond that they melted and floated towards the surface. Okay, the other rocks on the moon, we got white rocks, and so we've got black rocks, okay? The black rocks are the lunar maria. These are lava flows, much more common on Earth than the anorthosite. And these lava flows are volcanic melts from the lunar mantle. And you can see that they have a circular pattern in many places here, okay? And that is because this magma rose up to the surface and flooded large impact basins. The near side of the moon that we see from Earth has many large impact basins. And we now also know that this material, these black rocks, are considerably younger than the white rocks. We'll talk about that in a second. Okay, what else do we know? Okay, the near side and the far side of the moon are different, okay? The moon is in something called synchronous rotation, which means it always shows us the same face. This is going to be important for our discussion of how we had to go about measuring gravity. And we've got a lot of these lava flows or maria on the near side, very little on the far side. And we don't actually very well understand why this material is on the near side and so little is on the far side. It used to be thought that there were big impact basins on the near side, but not on the far side, but actually the biggest and deepest impactor on the moon is on the far side. It's called the South Pole Aitken Basin. It's about 2/3 as large as the United States. And if we had the idea that magma in the moon rose up to some sea level, so to speak, it certainly would have filled this up as well as these areas, because this is deeper than any of those basins. The difference between the near side and far side of the moon was actually one of the motivations for doing the Grail mission. Up to that point, there had been over 100 missions to go to the moon. The nations of Earth collectively had sent over 100 missions to the moon. As was talked about in the introduction and earlier in my talk, some of these orbited, some of these landed, astronauts landed and brought back samples. Some missed the moon completely, some hit the moon and couldn't stop, like Ranger 7. But over 100 missions to the moon, and we still didn't know why the near side was different than the far side, okay? So, you know, when I do science, I like simple questions, okay? And so if you sent 100 missions and you still don't know why one side's different than the other, you're looking in the wrong place, okay? And so my idea is that we needed to look inside the moon to find out what that has to do with this puzzle. Okay, so we'll come back to that in a second, but we're going to talk. This talk is basically going to be about volcanism and impacts and their role in the history of the moon. We now know, because the astronauts brought back samples that were highly shocked, evidence of hypervelocity impact, that nearly all the craters on the moon are due to impacts. And impacts are important in planetary evolution for two reasons, okay? The first is that the very largest impacts impart a great deal of energy into the moon and are a very important early heat source, okay? But those are only the handful of the largest impacts, okay? Then you got all these other guys, okay? All of these impacts occurred. These essentially are mostly very old, and they are material that impacted, and this was essentially the junk that was left floating around after the planets accreted, okay? Impacted the moon. And what scientists do to tell the ages of planetary surfaces is they go in and they count the number of impacts of a given size in a given region, okay? And so if you've got a lot of craters in a region, it's old, and if you have not too many craters within a region, it's young, and that's how we know the highlands are older than the Maria. So this is really pretty simple, okay? But the moon is extremely special, and that is because we have astronauts who have brought back samples from known locations that we have taken into a lab and looked at the decay of radioactive elements within them, which tells us the absolute age of the surfaces, okay? And so, so we can take this relative time scale provided by the craters and calibrate it with samples from Apollo. And so, so the moon, so we know that the lunar highlands are more than 4 billion years old, and the Maria are as young as 2 and up to about 4 billion years old. So these, this volcanism here that filled these impact basins was younger than the highlands, okay? Now, you might ask, Earth is right next door, and what was happening to Earth while all these impacts were hitting the moon? Okay, well, Earth was getting bombarded in the same way, okay? And in fact, Earth is a bigger gravitational target. And so if we look at the history of Earth, we talked about large impacts on the near side of the moon, okay? At the time, at the age of those large impacts, that was the time on Earth when the first life forms, the first prokaryotes, were in the oceans, okay? So at that time, Earth was undergoing the same kind of impact bombardment, okay? So goodness knows how many times life on Earth got wiped out and had to arise again because of massive heating associated with these large impacts. So the early Earth was a very violent place. We don't see this impact record on Earth. Okay, very hard to find craters on Earth, okay? Seafloor gets subducted, and there's no seafloor older than about 200 million years on the Earth. The craters that are preserved, here's a relatively young one in Meteor Crater in Arizona that's about 1 kilometer across. There's on the order of 100 known impact craters on the Earth. They're kind of hard to find. They're mostly found in very old regions. This one up here is an interesting one, Manicouagan crater in Canada. This crater wasn't known until the Canadians built a power plant and dammed a river, and this circular pattern appeared, okay? And turned out it was a large impact crater, okay? And so this record doesn't exist on Earth. We don't have surfaces on Earth that are as old as surfaces on the moon. We have handfuls of mineral grains that date back from that time, which tell us actually that we know that the Earth had an ocean very early on, but we don't know the role of impacts in affecting the Earth's crust. And so a good place that we can study that is the moon, because that record is preserved and it is relatively accessible. Okay, so that's the old moon part of it. And so now we're going to talk about some more recent data. All right, so let's talk about the impact record again. So we have, this is a map of the topography of the moon. Again, Earth once looked like this. This topography was measured by the Lunar Orbiter Laser Altimeter, which is another of our experiments, which is, it's up here, and it is mapping the moon as we speak. And the topography of the moon we now know better than we know Earth's topography. Okay, it's a very well constrained data set. So we can put the students to work, and we can. One of the things that we might want to know about the moon is where is the oldest surface on the moon. Okay, we've brought back samples, but only from a half dozen locations. Where are the oldest surfaces on the moon? Well, you can count the craters. Okay, so this is just all the craters on the moon greater than 20 kilometers in diameter. We've actually gone down to lower diameters than that, but the oldest areas are right in here and right back there. So if we ever wanted to bring back a sample of the oldest part of the moon, there we would be able to do it now. You can also see, so the near side of the moon that we see from Earth, I should say, is in the middle, and the far side that we don't see from Earth is on either side. So this again shows the high density of craters here, and then it shows this area has been volcanically resurfaced and has subsequently accumulated fewer craters and is younger. Okay, you can go down and you can see craters at smaller and smaller and smaller diameters. Okay, let's go in. Let's take a look at this area right here, and we can zoom in. And this is from the Lunar Reconnaissance Orbiter camera, and you can see this is the Apollo 14 landing site. This is the lunar module right here. We can go in even farther on this, and you can see that the closer that we look at the lunar surface, the more and more small craters that we see. These craters collectively have fractured the lunar surface. We know that. We will talk a little bit more about just how much fracturing has occurred. Something else is special about this surface, though, for anybody who is a golf fan. This is the first fairway on another planet, okay? This is Alan Shepard, who took a contraband golf club with him to the moon. And the ball went a far way, okay? All right, so that's the surface of the moon. That's how we use impacts to get ages of surfaces. And you can see that with all of these very small impact craters here, you get very good statistics. So we can do a pretty good job of getting relative ages, even within small regional areas. And we use all of this information to go back and to reconstruct the geologic history of the moon. But as I said before, there was a piece of the puzzle missing, and that piece of the puzzle was what was going on in the interior of the moon. And so to study the interior of the moon, we decided that we would use gravity, okay? All right. So when I proposed Grail, I had some people say, Maria, the general public is not going to get this because people don't understand gravity. Okay. All right. So how many people in the audience don't know what's going to happen to Wile E. Coyote? Okay. Okay. All right. Okay. See? Okay. You all understand gravity to some level. Okay. All right. And I am going to tell you more about gravity. Okay. So we decided to measure gravity using this two spacecraft mission, and the way that the reason that we used two spacecraft comes from the very special situation because the moon always has one face looking at us, okay, and we don't see the backside of the moon directly. So, so the way that we would measure gravity around a planet that doesn't show its same face to us all the time is really very simple, and you don't even need an instrument, okay? Every spacecraft has a radio on it, okay? And the radio has a known frequency. And when the spacecraft is in orbit, the planet is rotating beneath it, so you always see the whole planet by just waiting for the planet to rotate on its axis. And as the spacecraft comes towards you, the signal gets blue shifted, and as it goes away from you, the signal gets red shifted, okay? And this is the same thing as if you have an ambulance, and the signal gets higher as it's coming towards you, and lower in frequency as it goes away from you. And that's something called the Doppler shift. And the Doppler shift, if you had high school physics, not even high school physics, it could be middle school physics. Doppler shift gives you velocity, and if you look at how the change in velocity is acceleration, and acceleration has units of gravity, okay? So, so all we have to do to measure gravity is account for all the accelerations that aren't due to the gravity field of the moon, and then what we're left with is gravity of the moon. Okay, so if the spacecraft does a maneuver and fires a thruster, that accelerates the spacecraft, so we have to subtract that away. Or if this planet has an atmosphere, you have drag. Atmospheric drag is an acceleration, so you have to account for that. We actually, in our work, we also account for the little things like the gravitational attraction of all the other planets in the solar system. We make all the general relativistic effects. We even account for, well, we account for the Earth's ionosphere effects and bending the signal when it comes back. And we even account for the tectonic drifts of the plates that the tracking stations on Earth are on. But it's a really simple measurement. You just have to make a lot of corrections to it. So, but it doesn't work if you can't track the spacecraft from Earth, if you can't see the spacecraft from Earth. So when the spacecraft's on the far side, you can't track it. Okay. So what do? So we take two spacecraft and we let them track each other. Okay. And so what we do is we just take the distance between the two spacecraft and how that changes, and that gives us the velocity, and then we look at how that changes, and that gives us the acceleration. So we just let the two spacecraft chase each other around the moon, and the moon rotates underneath them, and then when you have a big gravitational mass, either on the surface or beneath the surface, the first spacecraft speeds up relative to the second one, and then when the second one gets affected by the gravitational mass, it speeds up and catches up with the first one. So you just get this accordion pattern all over the moon. And so all we're doing here is measuring the distance between 2 points, okay, and how that changes, okay? So it is an exceedingly simple measurement. It's just like what you would do in middle school geometry, okay? And the only thing that actually makes it rocket science is that we actually make this measurement to 0.05 of a micron per second, okay? And we beat our spec by a factor of 5. So, so we designed it, and it worked a little better than we thought, okay? Okay, so we do that, and actually the only thing that was really complicated about this is that if you have two spacecraft and you're trying to figure out distance change, the thing that's really important is having the timing down on the two spacecraft. So the two spacecraft need to have a really accurate clock. And it's getting hot and it's getting cold, and so the clock drifts. And if you were going to do this in Earth orbit and there is a dual spacecraft measuring gravity in Earth's orbit. It uses GPS, and we don't have GPS at the moon, so we had to figure out a way around that. And that's about the only clever thing that we had to do. But we make this beautiful map, and this is a map of gravity anomalies. And these, here the red correspond to gravity excesses. So if the moon was a billiard ball, the whole thing would be yellow, okay? And red corresponds to more mass than average, and blue and purple correspond to less mass or mass deficiencies, okay? And these big red areas are, this is the near side of the moon in the center, and again, the far side on either side. And these big positive mass anomalies are called mascons, and these actually tugged the first spacecraft, both first satellites out of their orbit. It was like a bumpy plane ride because the moon's gravity field is very bumpy. Okay, but we want to see inside the moon. Okay, and that's really easy. Okay, so this is how you see inside the moon with gravity. So you take your gravity map, which is from the last chart there, and we take this topography map that we got from the Lunar Reconnaissance Orbiter, and we subtract away the gravity that would be due to all of this topography, and then what we're left with is gravity that comes from inside the moon. Okay, and so that lets us look inside the moon. Okay. So one of the things that you can see in this map, once you subtract away the gravitational attraction of topography, this is something called a Bouguer gravity map, is there are lots of red bullseyes here, okay? This occurs, we used to think that these were the lava flows that are more dense than the white highland rocks, okay? That's a part of the contribution. But we found out that these anomalies are way too big just to be due to those lava flows. And what happens is the lunar highland crust, the white part, is very low density. And when these are all impact basins, and when the impacts occur, it excavates the moon's surface. Stuff from the mantle comes up and replaces it beneath the crater. And the rocks in the lunar mantle are more dense than the rocks in the crust, so we get these big anomalies. And so I said one of the interesting things that we want to know about the moon is how many large impacts we have, because these put a lot of energy into the moon. So there had been debates about how many large impacts there have been on the moon, because if we know the number of large impacts, we can go back and figure out how big the impactors were and what the flux was that was hitting the surface. And this basically tells us about the dynamics of the early solar system. Okay, what was left over after accretion. So we can go in now and figure out, okay, when we had all those craters on the surface, okay, there were hypothesized craters. Was there a crater here? Well, there are so many craters in some parts of the lunar surface that it's what we call in a state of saturation, which means there are so many there that if you can't accumulate more craters on the surface because it wipes out whatever's there, okay? And so you can actually lose the record of craters that are on the surface. Okay, so but now we know where all the craters are, okay? So here's a basin that we knew about before, and it's got a big anomaly associated with it, so that's pretty clear. But here's one that's not so clear. So here, we thought this was a crater. This doesn't look like it was a crater, but it is, okay? And so it was, so we were able to go through and get the inventory. Here's a strange one. This is on the far side of the moon. It's a basin called Moscoviense. And it's got a funny shape to it, and so there was the question of, was this really a low-angle strafing impact? Well, you just use a little processing here and sharpen it up, put a filter on it, and you see it was actually a double impact. Okay, so we can go through now, and we know the population of impactors on the moon very precisely. Okay, so I now want to go back and talk about these big basins here, because we got this one big one on the far side that we don't see from Earth, and this is the near side again. And the basins on the near side are, on average, bigger, okay? And it turns out the basins on the near side, this area here is where all those lava flows were. This is something that we call creep terrain, and here creep stands for potassium, rare earth elements, and phosphorus. And these are heat-producing elements which indicated that this area was hotter earlier in its history, okay? And isn't it interesting that the bigger basins are in this area that was hotter? So, okay, so let's go and let's look at the number of basins we have at a given diameter as a function of diameter. And here's the far side, and here's the near side. And this is just doing what you can see in the picture, is that the basins indeed on the near side are bigger than on the far side, okay? And you can do a little bit of statistics that tell you that this is probabilistically unlikely, that it's accidental, okay? So we decided to do a little work to say, okay, well, does the fact that this area was warmer on the near side here early in lunar history, does this have anything to do with the size of the basin? So we did a thermal model. So this is a model of early temperature on the moon, assuming that the moon had a plume, a hot plume of material. And so we could calculate what the temperature is. This is the side that's looking at Earth. This is the side that is on the other side of the moon. And we took then, so we got the temperature, and then we took a computer code and took an impactor, a 90-kilometer impactor, and impacted it in the same velocity on the hot near side and on the cold far side. And the next figure is going to show you what happens, okay? So the hot near side is on the left, and the cold far side is on the right here, and the same impact produces an impact basin as much as a factor of 2 bigger when it's hot than when it's cold, okay? If we go back then and say, well, we got these big impactors in the hot area, if we said, all right, what if this was cold, how big would those impacts be? We could take the population of impactors and correct for that, and then you really don't see a difference in the impact basins between the near side and the far side. So this is actually important in understanding early solar system evolution. And the reason for that is because these large impact basins on the near side were taken as evidence for something called the late heavy bombardment, that there was a bunch of large impactors that got maybe perturbed out of the asteroid belt, possibly due to changes in the orbits of the giant gaseous planets early in their history. And they sent this population of large impact basins barreling in that made these impacts at a given time, okay? We now know that the impact bombardment that there was, that the size distribution of impactors was overestimated, and that the far side, if you want to know what the impact flux in the early solar system was, then the far side basins are a much more accurate indicator of impact history. Okay, so I can't say whether or not this proves or disproves that there was a late heavy bombardment, but what I have to say is that that whole concept needs to be reanalyzed in the basis of this new data. And by the way, the size frequency distribution of lunar impacts where we measure ages of the moon's surface is used to calibrate the ages of all the other solid planets in the solar system, because we have an absolute calibration for the moon. So the ages of all the other solid planet surfaces in the solar system need to be revisited. Okay, so this is a big deal. Okay, all right. So the other thing that we can figure out from studying the inside of the moon is how much of this white stuff, how much of this white anorthosite rocks there were. Okay, and these rocks are, as I told you earlier on, they're aluminum rich. Okay, and when we test models of the early solar system, of the formation of the Earth-Moon system, we look at the elemental abundances of different elements on the Earth and the Moon. Okay, and one of the elements that scientists look at is aluminum. Okay, and so this actually constrains what the parameters of this impact that formed the moon were. So there were two different ideas with regard to aluminum, and we didn't know how much aluminum there was on the moon very well. And in fact, this is the number of papers that said the moon has about as much aluminum as the Earth, that the abundance is very similar. And these papers said that the moon is enriched by 1.5 to almost 2 times aluminum. So if it was the same, it would indicate that this impactor, when it came in, mixed very well with the Earth, and that what was thrown off had a composition similar to what was left then in the Earth. If it was like this, and in fact that first simulation that I showed you of a Mars-sized body assumed it was like this, that it wasn't so well mixed, and that the abundance was different. Okay. One of the things that we learned from Grail was how much aluminum there was in the moon, and we now know that that is wrong. Okay. So we know that that scenario that I showed you doesn't work anymore. Okay. So scientists are revisiting this, and so there are some different ideas now. But one idea that works, which was also done by Robin Knupp. I'm going to show you a simulation where Earth did not, Earth did not get impacted by an early impactor that was size of Mars. It actually got impacted by something else that was the size of Earth. Okay, and it wasn't a strafing hit; it was head-on, so that it mixed extremely well. Okay, so here's that simulation. Okay, and all right, bad day for planet Earth. Okay, so this is the kind of thing that you can learn if you can study the inside of the interior of the moon, and more work is needed on this, obviously, but we've certainly contributed to the story. So what else can we do? Well, here's another nicer map of the moon after we strip off the gravitational attraction of topography, and now I'm going to sharpen it up by taking gradients of that map, and you see a bunch of lineations that are here, and it turns out that these large lineations, they're hundreds of kilometers long, okay, and they're seen in gravity, and you don't see them at the surface, okay. What we think these are dikes. They are, in fact, very, very large dikes that intruded into the lunar surface that provide, they're essentially magma-filled, lava-filled cracks that are evidence for the early expansion of the moon. And this is Earth, not moon. This is out west. This is shiprock, but it is a place where there was a buried dike that was eroded, and you can see it at the surface here now. And it had been hypothesized early that the moon may have expanded, but there was never any evidence that was seen at the surface. Okay, and in fact, if you go back here, you don't see evidence for these things at the surface because they're buried. And we think what happened is, as I told you, we think the exterior of the moon was molten, and then it solidified, but as it was molten, it heated up the inside of the moon, okay? And then when the inside of the moon was heated up, it expanded, okay, and produced these cracks, okay? And so we now know that, but we never saw any evidence for this, so there were questions about it, whether this really happened, and we now know that the evidence was beneath the surface. The other thing that we can do, and this is a paper that is in review now, this is the near side of the moon that we see from Earth again. The far side is on either side, and you can see this pentagonal pattern right here. These are lava-filled cracks, and this is the plumbing system that got all that material up to the surface that produced the lunar maria. So we found the magma plumbing system, okay? And this is a map of the heat-producing elements, and these, we believe, are cooling cracks from this warm material then cooling off. Okay, so you can see we don't have the whole picture straight right now, but we certainly, I think, have learned a number of things that have told us why the near side of the moon is different than the far side of the moon, and there's still a lot to be done, but have also informed something about how the Earth-Moon system formed. And so I will just end here with a nice picture of the moon rising over Washington, and again go back to where I started with the idea that I very much hope that the next time that you look up at the moon, you think of it not only as beautiful, but as holding the key to mysteries for not only how it formed, but also what the early Earth was like. And I'll stop there.
We have time for some questions. There are microphones in the aisle, and let me invite anyone who has a question to come to a microphone. Please.
In getting the accuracy in the Grail system and measuring the gravitational field, it would seem that part of the problem would be a relative velocity between the two satellites, and I was wondering how that relative velocity was managed so you could sort of subtract it out and you knew the effects you saw were from the gravitational field and not some initial closing or
Oh yeah, so we actually wanted the spacecraft to do a large-scale drift as well, and the reason for that, excuse me, is when the spacecraft are at different large-scale differences, it gives us different depth sensitivity beneath the surface of the moon. So, so the answer to your question is just the least little bit technical, okay? So we use two radio signals between the spacecraft. One is a Ka band system, which is at 32 gigahertz, which gives us the distance between the two spacecraft. And then we have an S-band system at 2 gigahertz, okay, in which allows us to correlate the time tags between the two so that we can measure that drift. Okay.
Hi, I'm curious as to whether we understand the mechanism that gives the moon its synchronous rotation. It just doesn't seem like an accident that we have a near side and a dark side.
Yes, we do actually understand that mechanism, and to be a little bit unscientific about it, but I think it captures the spirit of it. Planets are like people; they're lazy, okay? And a planet wants to expend as little energy as possible, okay? And synchronous rotation is a minimum energy configuration in a planet that has a primary and a secondary, and in fact, the moon got into synchronous rotation within 10 million years after it formed. So, and so we have, in the outer solar system, we have cases, sometimes it's not synchronous, sometimes it's something that's called a resonance, and this happens if you have multiple satellites because they all interact with each other, but sometimes it'll rotate twice, for every time that it goes around, and the different moons will be some integer relationship between the two. But basically, in terms of the dynamics, it's a minimum energy configuration in the orbits. Yes.
Yes, I wondered if the Earth had differentiated in part before the impactor came in and led to the formation of the moon.
Yeah,
And whether that would affect the composition of the moon and
Yeah.
the composition of the moon after the impactor.
Yeah, that's actually that's a really good question. So we used to believe, okay, back in the day, that planets accreted homogeneously, and then they subsequently differentiated. Okay. However, okay, we now believe on the basis of studying the decay rates of certain isotopes that have relative hundreds of thousands a year half-lives, which is actually pretty short. We now believe that that the protoplanets that accumulated to form the planets were differentiated and differentiating as the planet was accumulated. So the planets were accumulated out of differentiating bodies, and they were differentiating as they were accreting. Yeah. So and it probably happened pretty quickly. So we believe that probably both bodies were differentiated at the time of the impact event.
Okay.
Let me ask the question that if you were to run those simulations longer, does the material that's tossed out coalesce?
It does coalesce into a moon.
It has to, you have to have that happen. That's why-
Sometimes more than one, right? And
Okay, yeah. Please.
When you subtract out the topographic effects, do you assume that the density of the material below is all the same, or do you look at where it is on the moon and make different,
Okay, so first of all, we know that the density of the dark stuff is more than the density of the lighter stuff, okay? We actually, I didn't talk about it because I didn't have time to talk about everything, but we actually have the ability to solve for the density, okay, of the material as we're doing the questions, as we're doing the calculation. So the gravity is somewhat non-unique. So we assume a uniform density, but we know what that density is, and you do see how clean that map is at short wavelengths, and so the moon actually is pretty well mixed due to all the impacts that were occurring. But we know what that density is. So, and actually being able to solve for that density is what allowed us to nail the aluminum content.
Okay, let's do the final couple of questions for the people who are at the microphones now. So please.
Hello. My question may be a bit off the line of discussion, but I, like so many people on the planet, have this affinity, an attraction, a love for the moon that I can't quite explain. And I wondered what kind of scientific ideas are out there that talk to something about what the moon does to us and what we hope from the moon. So much has been written, of course, and continues to be written about it. But I'm curious, in your scientific studies, do you uncover anything that could speak to that?
I'm not sure this is geology, but feel free.
Well, no. Okay, no, not no. I should stop there.
Do you want to say anything? Do you have any personal comments? I'm
No.
curious. I mean, what, is there anything that draws you spiritually to the moon?
So let me tell you one thing.
Please.
You know, when I decided that what I wanted to do was study the interior of the moon, they says, well, how can a mission ever be selected that doesn't have a camera on it to do photographic research? Because all missions have cameras. And I said, and my answer to that was, okay, the moon is a family member, okay? It's our close family member. Think of the people in your family, okay? It's not what they look like on the outside that makes them special. It's what is in the inside that makes them special. And that's what
That was a brilliant answer. Thank you very much. My question goes back to Wile E. Coyote, poor little thing that he is. As an Earthling, the information that you've developed appears to me to be dramatically useful to us on Earth in the sense that it might enable us to refine our ability to predict behavior of things like tides, like winds, like surface phenomena that we deal with. Is the moon a stable enough, static enough predictor that we can take your information and improve our overall predictions for behavior of our environment here on Earth?
So what, you know, I didn't talk about Earth-Moon interactions, okay? But, you know, one area that we can really, I think, make some headway is that the interaction of the Earth-Moon system is actually used in fundamental testing theories in fundamental physics, okay? And where we've kind of come short is we don't know what I'll call dissipation within the moon or the Earth in their very earliest history. And we don't have a lot of hope of going back and figuring out what that was, okay, before, you know, unless we know what it is today. And so for those studies, everything that I and other planetary scientists are interested in has to get subtracted away, and then whatever is left could be due to, you know, fundamental physics-like things, like variation in, like, the gravitational constant, or, you know, test of the equivalence principle. But, you know, understanding, you know, internal dissipation tides, you know, all of that comes into those calculations. So it is definitely my fond hope that we will make some advances in those areas. But this, as you can guess, this data is very complex to analyze.
And I thought I remember in your earlier beginning speech where you talked about the similarity between the patterns that you see beneath the oceans of the Earth and the similarity that you see on the moon, that perhaps oceanography and your work may have some meeting point here soon. We certainly are getting tired of the polar vortex.
Yes, sir.
Thank you very much.
So,
Our final question.
How did the MoonCam program work out? And
okay, sure.
do you feel that did you measure how it will encourage those students to be willing to pay for lunar exploration when they become adults?
Okay, well that wasn't the goal, but it would be a fantastic outcome if it happened. I just, you know, I wanted, so we had over 200,000 students sign up for the program in all 50 states, and the deal was that students would program software in their classroom that would tell you where the spacecraft was going to be at a given time. So they could take an image of something that they wanted to study, or they could take an image wherever the spacecraft is on their birthday, okay? And it turned out, and this was Sally's thought, and she turned out to be completely correct about that, as with so many other things, that it didn't matter whether it was a very, very high resolution image. The thing that really mattered was it was their image, okay? And actually what has surprised me is that I go to conferences now and I see students presenting original scientific research using the MoonCam images, and there was never any scientific requirement for it. I wouldn't have been able to afford to send it, okay, if I had put requirements on it, because it would have been too expensive to guarantee that I would make the requirements. So we are actually tracking, Sally Ride Science is actually tracking the progress of the students who have been involved in the MoonCam program. So I think within the decade, I know from having worked with a lot of these students that we have changed lives, and we will have some real tangible data to point to that. It's a very good database that we're going to continue to track.
That's a terrific story. Well, I think we're all going to think of the moon in a different way. So let's all thank Maria again for providing us with a fantastic evening. We're now adjourned.